back. This is unit 9.1, and in this unit, we're going to be talking about thermochemistry. And in your textbook, this is going to be pages 582 to 596, and in your workbook, 248 to 263. Thermochemistry. What is thermochemistry? Thermochemistry is the study of energy changes that occur during chemical reactions and changes in state. And this energy stored in chemical bonds is called chemical energy. So if we see here, we have molecules, very simple molecules. And remember, like say, for example, this could be sodium and this could be chlorine. So we have sodium chloride here. This sodium and this chlorine are held together by an ionic bond. There's a bond between these two elements. And let's say, for example, this is diatomic oxygen. Well, these two oxygen are being held together by a bond, and there's energy that is stored in those bonds. And when we start breaking these bonds, it starts releasing this energy, and then we can use that energy. So what I want you to keep in mind during this unit 9 is the law of conservation of energy, which is almost basically the same thing as the law of conservation of mass. Remember, we talked about that. Mass cannot be created or destroyed, only changed. Same thing with energy. Energy cannot be created or destroyed, only changed. So we're going to take the energy that's stored in these bonds, we're going to break that bond, it's going to release energy, and then we can use that energy for other things. For example, to fuel chemical reactions. So that's what thermochemistry is. And when we talk about thermochemistry, we talk about heat because it does release heat. Heat is represented by the variable Q, and the energy that is transferred from a warmer object to a colder object until the objects are the same temperature. Okay, and the objects are said to come to a thermal equilibrium. So we're going to look at the transfers of heat between objects. This heat is measured in joules, and that's represented by a capital J. And when we talk about heat exchange, we're going to talk about that in reference to the system and its surroundings. So say, for example, here we have an ice pack. Let's think about the ice pack as the system. And this ice pack, since it's colder than the surroundings, the heat energy is going to be going into the ice pack. This ice pack is going to absorb heat energy from the environment to try to warm up to come to a thermal equilibrium. And it's absorbing that heat energy from the air and from your skin. So if you were to put this ice pack on your skin, it's going to absorb heat energy from your arm, from your body, into the ice pack. And then so when you take the ice pack off and feel your skin, it's going to feel cold to you because that energy, heat energy, has, for the time being, left your body and gone into the ice pack. These ice packs don't last forever. Eventually, they are going to reach a thermal equilibrium, so it's going to be the same temperature as its surroundings, and then it doesn't work anymore, and we throw it away. So when heat energy goes into the system, we say that's endothermic. Okay, so let's look at this word, endothermic. Thermic means heat. Endo means going to the inside. So heat is going to the inside of the system. Now, opposite of that, we have here a fire where the heat energy in the fire is being given off to the surroundings because the surroundings are at a lower temperature. So heat energy always travels from a higher temperature to a lower temperature. So here this fire is very, very hot. So the heat is leaving the fire, going to the surroundings. And this is how we heat our homes, whether you have a space heater, either electric or gas in your home, or whether we have central heating, which is in your attic. There is some type of heat source, whether it's burning propane in a fire and then having that heat up the air and we blow the air through our house, or whether it's a space heater stove that just heats up the air around it, and then as we move through the house, it circulates that warm air. So when heat is leaving the system to the surroundings, that's called exothermic. Thermic again meaning heat. Exo means going to the outside or outside. And here we have a nice chart that we have all of this information in one place. We're going to talk about some examples, pictures and descriptions, which we already have, the equation associated with endothermic and exothermic, and the units for this. So if you'll pause the video and write this down, we'll talk about it. All right, endothermic and exothermic, some examples. Here, dissolving ammonium chloride. Well, in order for ammonium chloride to dissolve into an aqueous solution, heat has to be added to that. And it's going to get this source of heat either from putting ammonium chloride in a beaker and putting it on a hot plate, or from the surroundings. But heat is going inside the system to force this or to allow this to become an aqueous solution. And another example of that, of an endothermic process, would be the melting of ice. So we have an ice cube that's very, very cold. It's going to absorb heat, and as it does that, it's going to melt and change into water. So this ice is absorbing heat and going to water. Now, this is why we put ice in our drinks, because we like our drinks to be cold. They taste better. So we add ice to this drink. This ice absorbs heat energy from the drink and cools the drink down. Now, opposed to that, on the exothermic process, like dissolving calcium chloride. If we dissolve calcium chloride, what happens as it dissolves and as these bonds are broken, then it heats up the liquid. So if we had a thermometer that we put in the beaker as we dissolve calcium chloride, we're going to see that the water increases in heat. So this calcium chloride is transferring the heat to the water. Okay, so that's going to increase in heat. And that's just like freezing water. We put water in our freezer, in our refrigerator freezer, and our freezer is at a lower temperature than the water, so it draws heat away from the water. And as it draws enough heat away from the water, if it's a low enough temperature that it reaches the equilibrium, if it's below 0 degrees Celsius, then that water is going to become ice. So your freezer is drawing heat off of this water. So there's really no such thing as hot and cold. It's just hot or less hot, because we're not adding cold to the water, we're removing heat from the water. Okay, so think about it as a heat. We're either adding heat or removing heat. All right, and we've already talked about the picture and the description, the ice pack and the burner. So let's talk about the chemical equation. For an endothermic process, you are always going to see heat as a reactant. So here we have A plus heat yields B. Heat is a reactant. And since in chemical equations we don't use minus signs, for an exothermic, remember exothermic means that heat is leaving the system, so we can't say A minus heat because we don't use negative signs, we use always plus signs. Then if we move this heat over to the product side, then it's a positive, because if it's a negative, remember when we draw it across the equal sign, it's going to change signs to a positive. So in an exothermic process, heat is always a product of the reaction. So you're going to have A yields B plus heat. And for your units, it's always measured in joules, capital J. Okay, and this Q, heat quotient, is always in an endothermic process going to be larger than 0, which means it's a positive number. And because we're adding heat to the system, a positive number, adding heat to the system. And opposed to that, Q is going to be less than 0 or a negative number, because remember, heat is leaving the system, leaving, negative, leave. So think about leaving the system as negative. It's always going to be a negative. So exothermic process, you're going to have a negative Q or negative joules, a negative number on an exothermic process. So if we look at that graphically, remember, this is an endothermic process graph that we're looking at here. Enthalpy, let me write this word so you can see it. Enthalpy is a change in heat in a system. So here, if this y-axis is the potential energy and here is time, at the beginning of this process, we have some reactants that have this much energy. Okay, and then as time goes, as we add energy or it absorbs energy from the surroundings, when it hits this peak, this is where the reaction starts. So this is called your activation energy right here, activation energy. And then as this chemical reaction is activated, it's going to proceed. And then when it finally finishes here with the products, you have this much energy. So if we look at this and continue this line over to the y-axis on your graph, you're going to see here was the initial energy. Here is the final energy. So the final energy is higher than the initial energy. That means that this system absorbed energy and stored it. Endothermic process, energy went in. So we have this difference here that's called delta H, or the change in enthalpy. It's always a positive number. See, positive energy. Okay, this is also called, delta H is also called the heat of reaction. This is the heat of reaction. It's a positive number. Now, a good example of an endothermic process is plants going through photosynthesis. And these plants take this energy from the sun. So remember, energy can't be created or destroyed. So plants take the energy from the sun. They use some of that energy to grow and become bigger, and some of that energy is stored. And plants store energy as fruit. And then we can now eat this fruit. We take this energy, we process it, we break down those sugars. Some of that energy we use to grow. Some of that energy is used for us to move around, move our bodies, move our muscles. So everything is just an energy exchange. Now, opposed to that, we have an exothermic process, and this is what the graph looks like for an exothermic process. And let's compare those two. So here's the endothermic process. Let me clear up all the writing. Endothermic process, so it still has this hump, which is called the activation energy. We still have these two flat areas, but look at the difference. Exothermic, endothermic, exothermic, endothermic. So in an endothermic process, you start with a certain amount of energy and you end with more. In an exothermic process, you start with the amount of energy, and when you end, look, it has less energy. So if we look at that, if we continue this line across, we're going to end up with less energy because this heat has left the system. Okay, and so we have a change in enthalpy, or the heat of the reaction is a number less than 0 or a negative number. And a good example of that is an internal combustion engine that we use in our cars. So we take this gasoline and put in our car, and this gasoline is a form of energy. This gasoline is burned. It combusts inside the piston chamber. And when it does, it moves this shaft here, turning this wheel, this gear. This gear turns other gears that are eventually connected to our wheels that make the car go forward. So this energy from this gasoline is used to do work. Now, we also have a lot of heat that's generated here. And this oil that we see down here, it lubricates all this so that this metal doesn't heat up and start warping, because that would ruin your engine. So you have to make sure you have oil in your car for lubrication of all these moving parts. But also you have your radiator. There's channels here that are all around your engine where water flows through these channels. This water absorbs the heat energy from friction and combustion, because these are moving parts, that's friction. And then it's transferred back to a device in your car called the radiator, which has a bunch of small tubes. And what's behind the radiator? A fan that's blowing air. So it blows air across these tubes. This air then absorbs the heat energy from the water and blows it out into the environment. So it cools down the water so the water can recirculate and absorb more heat energy, and it's just a circular process. Now we know that it absorbs energy. The air absorbs energy and is then blown into the environment, because if you stand in front of your car where the radiator is, you can feel heat, hot air coming from your car there. All right, so heat plus work is delta H, the change in enthalpy. Some of this is heat and some of this is work. Added together, still the energy in the universe is the same. It's not created or destroyed. It's only being transferred. Some is work and some is heat. All right, so what you have to remember about these graphs is that on an exothermic process, the products over here are lower energy than the reactants. And on an endothermic process, it's just the opposite. It stores energy, so the products have higher energy, the reactants have lower energy. All right, finally, heat capacity. Heat capacity is defined as the amount of heat that's needed to increase the temperature of a substance by 1 degree Celsius. So there's two things that this is dependent on, this heat capacity, and that's the mass of the substance and the composition. So say, for example, we're talking about water. If we take just a glass of water and we go set out beside our pool, this water we may have gotten from the refrigerator, so it's at a nice cool temperature. But as it sits there in the hot sun and absorbs energy, remember, it's trying to come to an equilibrium temperature. So as it absorbs this energy, it warms up. And so eventually, maybe 30 minutes later, this nice cool glass of water now is a warm glass of water. But you're sitting out by the pool, right? So here we have, 8 ounces of water? And then in your pool, you may have 17,000 gallons of water. So this mass is a lot bigger than this mass. So it's going to take much longer for 17,000 gallons to heat up, absorb energy to heat up so that you can go swimming. So now at this point, you may be sitting by the pool. It may be warm enough for you to, put your feet in the pool, but not necessarily dive in and, enjoy it to the fullest extent. So because this has a different mass, it's going to take longer to heat up. Also, if we compared now our water that we have in our glass, maybe some of you have a play set in your backyard, you have younger siblings, and now you have that compared to, say, the slide. Okay, so you have a slide, or you may have a slide on your pool. This is a different composition than the water. This is plastic. And so, or it could be metal or some kind of composite plastic material. But this is going to be a different composition now. And when this sits in the hot sun, this is going to warm up a lot faster than the water warms up. So, you may have a slide that's very hot, and in the middle of the summer, it may be so hot that it actually burns your skin. So it's a different composition, so it's going to heat up at a different rate. All right, so that's heat capacity, the amount of heat that's needed to increase the temperature of a substance by 1 degree Celsius. It depends on two things: the mass of the substance and the composition, what it's made of. And that brings us to, is it a conductor or an insulator? right? So a conductor of heat, a good conductor, is going to be like a metal. It changes temperature very easily. So that's why we have our cookware is made out of metal, because it changes temperature easily. We put it on the stove, it absorbs the heat energy from the fire. That heat energy is then transferred to our food, which cooks our food. And an insulator resists change in temperature. So that's why we use insulation in our attic, because what happens is these particles of insulation, okay, whether it's the blanket type fiberglass or other material insulation, it's real airy, because what happens is it traps air. Okay, it's fluffed up, it traps air, and this air is a good insulator. Okay? It resists temperature change. That's also why birds, when they get cold in the winter, you may see a bird that will sit on the fence or something and shake and fluff up its feathers and get real poofy looking. That's because it's trapping air between its feathers, and then its little body can heat up that air, and then it's like, a blanket being around, a blanket of air. Another example of that is during the winter, if you have clear skies, then the earth is going to lose a lot of heat to the atmosphere. But when it's real cloudy, you have this nice poofy clouds that are around the earth, and these clouds act as an insulator. So it holds in the air. So if it's nice and cloudy, the temperature is not going to change very much. So that's why the desert gets really, really cold at night, because you don't have these clouds, and so the earth loses a lot of heat to the atmosphere. And then during the day, since there's no clouds, then it heats up really, really, really hot. And vice versa. If you have a cloud cover, okay, the heat can't get through, because this is an insulator. These clouds are insulating. And so when you have a lot of clouds, the temperature of the earth during the day doesn't get as hot. Okay, so conductors and insulators. All right, so let's talk now about specific heat. This is what we're going to be using a lot of in this first section here, is specific heat, and that's represented as C sub P. Okay, and a lot of times just C, we drop that sub P off. Specific heat is the energy that's required to change the temperature of a substance 1 degree Celsius. 1 gram of the substance. So this is almost exactly like heat capacity. Heat capacity doesn't specify a specific amount of mass, where specific heat does. It says 1 gram. So this is no longer general. This is heat capacity as a general definition. Now we're getting specific, specifically 1 gram of the substance by 1 degree Celsius. Okay, and the unit for this is joules. So remember, that's heat. How much heat does it take to raise 1 gram 1 degree Celsius? So joules per grams degree Celsius. So the unit for specific heat is joules over grams degree Celsius. Now this specific heat is only good, this number is only good within a certain phase of matter. Like, we have a specific heat of water that we're going to see a lot, 4.18 joules per grams degree Celsius. This is only for the phase, liquid phase, water. Okay, ice has a different specific heat. Ice absorbs energy at a different rate, and we're going to talk about that in our next section. So this is only good within a certain phase of matter. Each phase has a different specific heat. So how can we use this? Well, first of all, we can use this. Another measure of heat is called the calorimetry. This is from the Latin word calor, which means heat, and Greek metron, which means to measure. So calories are measuring heat. So sometimes we measure the heat in our food, and that's represented as calories. How much energy can you get out of that food? All right, so 4 things happen when heat is transferred. It can either change the temperature of something, it can change the volume, which we're not going to discuss in this unit, It can create a change in state, which it can go from solid to liquid to gas, or it can cause a chemical reaction to happen. So the formula that we're going to be using for this section is Q is equal to mCp or C delta T. Okay, mC delta T. That's how I remember it. MC delta T. It's MCAT. MCAT C, and this looks like an A, but it's really a delta T. MC delta T. Where Q is heat, and that's measured in joules. M is mass, that's measured in grams. C sub P is specific heat, and that's going to be given to you. Every substance has its own specific heat. Like, say, for example, aluminum may have a specific heat of 0.7, and copper is going to have, say, a specific heat of 0.3. So each substance has its own specific heat. And then delta T, delta means the change in. So anytime you see delta in science, that's something is changing. Delta T would be the change in temperature, and temperature is measured for this in Celsius. Sometimes Kelvin, so you have to watch out for that, but mainly it's going to be Celsius. So what types of questions are you going to see using this? How much heat energy? Okay, and we're going to be solving for Q if it's asking how much heat energy. What mass? So you're going to be given everything but mass, and you have to solve for the mass. Now that's just a simple rearranging. So if we have Q is equal to MC delta T, if we're solving for mass, okay, again, I like to put a square around what I'm solving for, lock that down. How do we get rid of C and delta T? Well, if we divide both sides by C delta T, okay, this side, it cancels out because remember what's on top cancels what's on bottom. So that leaves us with M is equal to Q over C delta T. Okay, and that's going to give us the mass. What is the specific heat? Same thing. So if we start out with Q is equal to MC delta T, specific heat is this. So if we divide both sides by M delta T, we're going to get C. So it's just a rearranging. What is the substance made of? Okay, that again is solving for specific heat, because remember I told you every substance has its own specific heat. So if we solve for specific heat, we can look this up on a chart. You'll be given a chart with a bunch of materials listed out, and then whatever number matches what's on that chart, that's what that material is made of. What is the final temperature? So here we're solving for temperature, and in this type of question, it could say that, your temperature starts off at 0 degrees Celsius, and we have the specific heat of water is this, and we have this much water, this much heat is added to it. So we're going to solve for a change in temperature. If we get a change in temperature that's equal to 20 degrees Celsius, what's the final temperature? Well, if it started out as 0 and it changed by 20 degrees Celsius, then the final temperature is going to be 20 degrees Celsius. Okay. What's the beginning temperature? Again, it could give you the ending temperature, and if it decreased by 20, then the final beginning temperature, is going to be 0. So you're just going to have to look and see what the question is asking and then use all you have. What is the change in temperature? So you could just be solving for the delta T, not a beginning or an ending, just the delta T. So let's look at some of those examples. All right, so pause the video and write this down in your notes, and then we'll work it out together. All right, how much energy is required to heat up 20 grams of water from 30 degrees to 50 degrees? And the C sub P, specific heat of water, is 4.18 joules per grams degrees Celsius. Okay, how much energy? That's what we're looking for. How much energy? All right, so let's list out what we're given here. 20 grams. Grams is a mass, so I'm looking for my M. Here it is, 20 grams, okay, of water from 30 degrees to 50 degrees. So this is a change in temperature. I know change in temperature is delta T, so I'm going to come over here and look at a delta T. Now you can either write 30 to 50, or if it's something like this, where you can do this in your head, you know that the delta T is equal to 20 degrees Celsius, the change in temperature. So it's the difference between your beginning temperature and your ending temperature. So delta T is the change in the temperature, which is 20 degrees Celsius. And then it gives us that our C sub P, which I told you, sometimes I drop the P off and just do C. Here's C, so it's 4.18 joules per grams degrees Celsius. How much energy? So we're looking for Q. Remember, Q is heat energy, okay, and this is going to be in joules. So what's our formula? Q is equal to MC delta T. We're solving for Q, so I don't have to rearrange this. So all I have to do is plug in now. Q is equal to M. Substitute in M, 20 grams. C, 4.18. And delta T Celsius. So our change is 20 degrees Celsius. Now, before you do this math, actually, we should have done this before we plugged it in. We need to make sure that all of our units are in the proper form. So mass is always in grams, so we do have grams, okay? Your specific heat, joules per grams degrees Celsius, joules, grams, Celsius. All right, so grams, that matches. Celsius, that matches. So we're going to end up with joules as our answer. And 20 degrees Celsius, it needs to be in Celsius to match the specific heat that has Celsius. So all of our units match each other, okay? And so we can plug these in now and get our answer. 20 times 4.18 times 20. So go to the calculator. 20 times 4.18 times 20. This is going to end up with 1.672 times 10 to the third. All right. 1.672 times 10 to the third joules. 10 to the third joules. All right, how many sig figs? Well, here's 3 sig figs. These 2 zeros count because there's a decimal there. 30, this zero's at the end. It's not going to count because there's no decimal. So we have 1 sig fig here. So we can't have anything less than 1 sig fig. So I don't even have to count here. So this needs to be 1 sig fig. So our official answer is 2 times 10 to the third joules. Now again, if you're taking this quiz on Canvas, Canvas can't do sig figs. So please look for this statement, 2 decimal points, 2 decimal places is what I actually say. So let me just erase that. A lot of you are not doing that when you take your quiz on Canvas, and it's going to count it wrong. Canvas is going to count it wrong if it's not 2 decimal places, because it's expecting 2 places after the decimal. Here's your first, here's your second. So it's expecting 2 numbers after your decimal. So if we were going to put this in Canvas where it's asking for 2 decimal places, the answer is going to be 1.67. This 2 is not going to bump this 7 up. 1.67 times 10 to the third joules. Okay, so depending on how you're taking your quiz, if you're taking your quiz on paper, officially the answer is going to be 2.0. But since Canvas can't do sig fig, can't count sig figs, it doesn't know how, 1.67, because I'm specifying here 2 decimal places. Okay, so if you put in any number than 1.67, it's going to count it wrong. So make sure you read and know how many decimal places I want your answer so you can put in the correct number. All right, let's do another one. When a 50-gram block of copper was heated with 1,046 joules of energy, the temperature increased from 10 degrees to 64.3 degrees. What is the specific heat of copper? All right, so let's identify our givens. We have 50 grams of copper, and this is our energy, 1,046 joules. It changed temperature from 10 degrees to 64 degrees. What is this specific heat? So that's what we're looking for. What is this specific heat? Well, specific heat is C. So I'm not going to put my question mark there. All right, 50 grams. Grams is a mass, so that must be my M. 50.0 grams. 1,046 joules of energy, that's Q. So I'm going to put 1,046, listing out my givens. Change in temperature. All right, so we started at 10 and it went to 64.3. So the change in temperature is 54.3 degrees Celsius. All right, so I have joules, grams, Celsius. Those are all the units that I need for this, so I'm not going to have to convert any units on this. So what is my equation? Q is equal to MC delta T. What am I solving for? Specific heat. So I need to pull M over here, and I need to pull delta T over here, which gets rid of it here. So to solve for specific heat, it's Q over M delta T. So let's think about our units for specific heat. Joules per grams degrees Celsius. Does this match? Well, Q is in joules, M is in grams, mass, delta T, temperature, is Celsius. So we have joules per grams degrees Celsius. So these are going to be the units for our answer, joules per grams degrees Celsius. All right, so let's plug in our numbers. 1,046 joules, 50.0, and 54.3. Okay, we already did our units, so I'm not going to put units in here. All right, so this is our math problem now. So we're going to take, and I am going to do box over a box like this. So I have 1,046. Okay, and this is going to be on the bottom 50.0 times 54.3. Enter. All right, so this is going to be 3.852 times 10 to the negative 1. 3.852 times 10 to the negative 1. So 3.852 times 10 to the negative 1 joules per grams degrees Celsius. Now, if I wanted this to be a standard notation number, then that would be 0.3 because we're moving our decimal place one time to the left, 852 joules per grams degrees Celsius. Officially, our answer is going to be how many sig figs? We have 4 here. We have 3 here, 3 here, and 3 here, so it would be 3. So officially, our answer is 0.385 joules per grams degrees Celsius. But if I was doing 2 decimal places for Canvas, 2 decimal places, your 0.3 is 1 decimal place, 8 is the second decimal place. So now I'm looking at this 5. Does this 5 round this 8? It does. So I'd be 0.39 joules per grams degrees Celsius. Okay, official answer, Canvas answer in standard notation, not rounded properly, answer in scientific notation not rounded properly. Okay, so there's a lot of steps there on the answer. All right, one more. What is the final temperature when 90 grams of aluminum at 0 degrees Celsius absorbs 500.0 joules of energy, and the specific heat of aluminum is 0.897 joules per grams degree Celsius? All right, what is the final temperature? All right, so we're solving for delta T here. Actually, we're solving for delta T, and then we're going to solve for final temperature. So we're given a Q. Q is heat, 500 joules. We're given a mass, 90 grams. And we're given the specific heat, the C of aluminum, 0.897 joules per grams degree Celsius. All right, so Q is equal to MC delta T. We're solving for final temperature, so we're solving for delta T. We're going to use this 0 degrees Celsius here in just a moment. So we need to get rid of MC, mass, and specific heat. So we're going to divide both sides, pull it over here under divide. All right, so let's check our units. J should be our heat, and it is. Mass should be in grams, and it is. And this is joules per grams degrees Celsius, so all the units match. So that means we're going to get our temperature in Celsius, which is what we have here. So we're not going to have to do any conversions. We're just going to have to do some subtracting when we get our answer. So now we can plug in our numbers, 500 over 90 times 0.897. So that's our math problem. And this is going to give us our delta T, not our final temperature, our change in temperature. So to answer this question for final temperature, there's one more step we're going to do, but let's get this first. So 500 okay, and what goes on bottom? 90 times 0.897, so 90 times 0.897. All right, we're going to get 6.19348. Okay, 6.19348. Is that right? 6.19348. 1934.8. Okay, good. Just verify. All right, so our change in temperature is 6.19348. So we're not going to round or anything because this is not our final answer. We only do our rounding when we have our final answer. So it wants to know what the final temperature is. Well, if it started out as 0 and the change is 6.19348, then we're going to have to take the difference in this. So the difference between 0 and this is 6.19348 degrees Celsius. All right, how many sig figs? Well, this is 0 sig figs. This doesn't have any sig figs because it's just a 0. But we can't have 0 sig figs for our answer. So we have to look at the other ones. So this is 3, 3, and 4. So this is just 3 sig figs. So 1, 2, 3. So this 3 is going to tell us whether we round. 3 doesn't, so we're just going to drop that off. So our official answer is 6.19 degrees Celsius. Okay, 2 decimal places. Well, this is 2 decimal places. Okay, so official answer. Our Canvas answer would be the same thing. Okay, 2 decimal places. All right. Okay, so now we have a concept question. I want you to think about this, and I'm going to show you some techniques on how to answer some concept questions. Let's read the question. It says there are 2 50-gram bars. So we have 2 bars of metal that are the same mass. one copper and the other aluminum. Okay, so one copper and one aluminum. Explain your answer without doing any math. So if the specific heat of copper is 0.385 and the specific heat of aluminum is 0.897, which bar is going to require less energy to change the temperature by 10 degrees? Okay, so 10 degrees, both of these have to change by 10 degrees. So MC delta T, because it's asking energy, all right? MC delta T, all right? So which is going to require less energy without doing any math? So without taking the mass, which is 50, multiplying it by the specific heat, which is 0.385 times the change in temperature, which is 10. Let's just think about, what if the mass was only 1? And what if the temperature was only 1? Okay. So on both of these. Well, this is easy now to do in your head and to see that how much energy it's going to take. So what I did was I took this mass and I made it a simpler number, like 1. And I took this temperature, which is a simpler number, that's 1. And I'm multiplying this number by 1 and by 1, which doesn't change the number. So if this is 0.385 and this is 0.897, if we multiply 1 by these, we're going to get this number. So that's how much energy is required. Multiplying it by this number, 1 and 1, I'm still going to get this number. So that's how much energy is required. So now I can compare these two on simpler terms. This is a smaller number than this. So this one is going to require less energy than this one. Okay, I didn't do any math really with the calculator. I mean, it says without doing any math. Well, you're going to have to do some math, but easy math in your head. I can see without picking up a calculator that the copper bar is going to take less energy to heat up than the aluminum bar. This one only takes 0.3, this one takes 0.8. So if you just simplify the question like this, because you know you're multiplying here, then you can get this without picking up a calculator. Now, another thing I want to point out is the lower the specific heat value, the lower the value, that means it requires less energy to heat that up. Okay, so it's going to heat up faster with equal amounts of energy. Okay. All right. All right, that's it for this section. So make sure you slap that like button right across the face. Make sure you subscribe and make sure you click that notify so that you know when I put up other videos. Maybe I'll work a video or work a problem out on a video that I don't necessarily have in Canvas, but that could help you.